For this example, we are going to use the method of composite shapes for solving for the centroid. And with composite shapes, in order to be able to do composite shapes, we have to look at the object itself that we're trying to find the centroid of and look to see if it has what we call nice shapes. And those nice shapes mean that they are squares, circles, that type of thing. So if you look in the back of your book, you will see these tables, and these tables have what we call nice shapes. I'm going to just look in on the rectangle itself. And if you look at the rectangle, it tells us where the centroid is. That's what the C value is. It tells us the dimensions from some reference axis, the XY axis, to the X prime. X prime is the centroidal axis, but it's from this relative surface here is where everything is measured from. So it gives us these dimensions. If we quick look in at a triangle, we see that it's this 1/3 distance from the high side, which kind of makes sense. Our centroid would be closer to the area that has more space. Okay, so let's look at this and let's see how this relates to composite shapes. If we use composite shapes, we can have objects that may have multiple shapes attached to them. They could have a square, a triangle, maybe it has a hole in it, a semicircle, something like that. These are all different shapes. And what we can do is use this formula here to find our centroid in the XY bar location, summing up each of the different composite shapes that we have. So in this case, this could be shape 1. We could have this being shape 2, the square. Shape 3 could be the center part, and shape 4 could be the triangle. So that could be the type of shape. So let's look at an example doing this. Here's an example of a piece of extruded aluminum channel, and what we're told to do is try and find the centroid of this object. We see on here that it has a set X and Y coordinate system, so everything will be relative to that coordinate system, and that's very important to note. It has to be relative to it. And if we look at it, we have a number of different types of nice shapes. It looks like we have rectangles and semicircle kind of thing going on. And there's multiple ways of setting this up. One way to do this is I could have a rectangle here on the outside as a shape. I could then subtract the green rectangle from it. And then I have this semicircle side here. That would be one example of a way of doing this. Another example would be to look at two rectangles instead. We can still use this semicircle here, and we could do a rectangle here as a shape, and then another rectangle over here, or we could change the way those are. I'm going to use the one where we cut out the middle one. If you go onto Canvas, you will see that I've done this example here with this red 1, 2, and 3 shape example. So that's another example that you can go onto Canvas and see how that is done. But I'm going to use a different way. Okay, here's our shape. You'll see in here I have set up this to be a shape of 1 for this blue large rectangle. I have shape 2 as my green one that I'm going to subtract, and then I have shape 3, which is the semicircle. This essentially can be broken out into this type of arrangement here. So you see that it equals essentially the blue one minus the green one plus the red one. Notice I left the X and Y coordinate system where they are relative to those shapes themselves. This will help us define the centroids of each of those individual objects. Okay, now that I've defined each of those shapes, it's time to look back at our formula. So again, our formula is this X bar is equal to the sum of the shapes of each of the shapes of their X tilde, their individual centroids, times the area divided by the total area. So see them both equations that the denominator has this same area. The best method that I like to use is this table format. I find that if students use this table, they tend to get the answer correct. If they just use the formula and plug and chug it, a lot of times things are missed and are done wrong. So let's take a look at this formula, or the table. So I've labeled it out as for each shape. If we look at the shape for shape 1, we see shape 1 has an area of 80 times 110. For shape 2, we have an area of, it's 20 minus 80, which is 60. So this is 60. I'll put it over here. And the overall length is 20, so this is 90 here. Sorry, the gap is 90. So this will be 60 times 90. And for shape 3, we see it has a radius essentially of 40 millimeters. And if you forget the area of a circle, we can look back at our table. And here on our table, you will see that the area is 1/2 pi r squared. So again, 1/2 pi r squared is 40 millimeters squared. And let's calculate each of these. Okay, so I've calculated the areas out on here. The one thing I want to point out is that you will see on here that this green area has a negative value, right? And that negative value is put in there because we are subtracting that area out. The next step is to find the x tilde, or the individual centroids. So if we look at the main rectangle, the blue one, we know from our graph, and we also know physically, that it's half the distance, right, from the side. So this is one distance, and then we have the other distance. This is essentially our distance to the x-axis. That's our y tilde. And then we have this distance here is our x tilde. It's the distance to the y-axis. And we said that this was 110, so it is half that is our x tilde. So we'll put in 55 millimeters, so this is 55 millimeters. Now in our green one, let's take a look at that. This distance, again, the centroid is here. That distance is 45. So to this edge is 45 millimeters. But we also have an additional amount of 20 millimeters. So our x tilde in this case is 20 plus 45, or 65 millimeters. Last, we have to look at our centroid for the round object, the semicircle. And that will be this overall distance plus this additional amount here, right? This is our x tilde for that shape, but then we need this additional amount of 110. Where do we get that number? Let's look back at our table. If we look in the table, think of this being turned sideways. This is the distance that we're looking for, this 4/3 r over pi. So again, this distance, I'm going to bring it down here, is 4/3 r over pi. We can calculate that in here. So remember, it's 110 plus 4/3 r, which is 40 over pi. So that total will be 120, we'll call it 127 millimeters. Okay, so that gives us the x tilde. While we're at it, let's do the y tilde and calculate that also. So for the blue rectangle, it is this distance coming down, right? and that distance, again, this side is 80, and it's down to 40, so half that distance is 40. But realize it is a negative 40 millimeters because it is below the x-axis, so the y value is below that. If we look at the green one, we see we again have this is 20, and then this is our y tilde here, and that is half that, which is 60 or 30. So we have here a minus 20, minus 30, or minus 50 is the location for that one. Last, let's look at our semicircle. This is this distance, this is our y tilde. That is equal to essentially our radius of 40. So we can just put that right in here as 40. All right, so the hard part is done, being able to find all those. Now it's just a matter of simple math where we take our x tilde times the a value, and then we will do the y tilde times our a value. I'm going to erase that. So all I'm going to do is take this x value here, 55, times the 8800, place that here, and do that for each of these, for the x values, and then the y. So then the y tilde times the 8800. I will do that real quickly. Okay, I've calculated those all out. Just a few comments. I originally forgot to put the negative sign on the y tilde, so make sure that is there. So look at this when we do the negative signs too. So I have this negative y value times the positive area, so this value becomes negative. Notice my area in the green one was negative, so a negative times my negative, or my positive x value gives me a negative x tilde a, but with my negative y tilde, it comes out as a positive value here. So be real careful with the positives and negatives, and it's very important to do it this way. The next step is to do the sum of all of our area. So that's adding up each of those. And if I do that, I should end up with a 5913.3. And then I can sum up all of my x tilde times a and my y tilde times a. Okay, so I've put all the values in and I've added them up for my x tilde a and the y tilde a. Please note that I had to change this value here. For some reason I multiplied this wrong. This value, this 2513 times the 127. It should be a 319,151. Okay, so now the next step is to use our formula from up here. We know our area, our total area. Now we know the sum of our x tilde a and our y tilde a, and we can find x bar and y bar. Okay, so here's our formula. Now we just plug in our values. We have this 452,151 divided by 5913, and that will equal 76.5 millimeters. And then last, for our y tilde, we have the values here of negative 182,520 divided by our 5,913.3, and that will get us 30.9 millimeters. Okay, it's very important now to kind of look at our answer that we have for this on where this centroid is. So this is the location of it, and let's see if it makes sense to what our object looks like. So if we go back here, let's take a look. It says that we are at 76, so somewhere out here in the X location, and then down 30. So here's 40, so we're somewhere in here. And that kind of makes sense. It might be a little bit more over to the right or so, but that seems to make sense for us for what we have. So this is down to a negative 30.9. We know it's not going to be right here because it has all this other material that's missing. So our answer looks correct.